So welcome everybody to our latest A2 video on trigonometry, and in this video we'll be looking at double angle identities, which is different to compound angle identities and definitely worth making a note of. Now continuing on from compound angles, and we take the sort of template diagram as you can see on the screen. So let's imagine that with compound angles we had this angle here, which we called as A or alpha, and we had this angle here, which we will call B or beta. Now what happens if, and from that we knew that we had these two trig identities when we were adding those two angles together. Now what happens if these two angles were the same? So for example, this was A and this was A. Now if those angles were the same, then the formula for sine A plus A would therefore be sine A cos A plus cos A sine A, which would indeed give us this double angle identity. And likewise, if we were using cos, so if A and B were the same, then cos A plus A would equal cos A minus sine A sine A, which would therefore give us a second trig identity for these double angles as cos 2A equals cos squared A minus sine squared A. Now if we then took on that, we know that sine squared A plus cos squared A equals 1, or sine squared theta plus cos squared theta equals 1, and using this trig identity here, so if I just quickly make a little note, so we've got cos 2A equals cos squared A minus sine squared A. Now in terms of notation, that's exactly the same as cos 2 theta equals cos squared theta minus sine squared theta. Now if I took this, or either of those two, whether working A's or theta, I can then derive, using our trig identity of knowing that sine squared A plus cos squared A equals 1, that if I then replace, let's say, and just get rid of this here, so for example, if I replace the the sine 2A with 1 minus cos squared theta in brackets, then what I would end up with is this here. And if I then went on to replace the cos squared theta with 1 minus sine squared theta, then that would give me this identity. So although these two aren't, let's say, more formal double angle identities, these are ones that you may come into question and use a lot more than the actual one that we are given. And then finally, in terms of double angles, if we convert tan 2 theta equals 2 tan A over 1 minus tan squared A, and where this comes from is we know that tan A plus A is going to equal tan A, and it's going to be plus tan A over 1 minus tan A tan A. And that's where we get our third double angle identity. So in terms of these are all trig identities that for double angles that you are going to need to know. And again, this could involve you solving equations, proving identities, or manipulating things. And it's also incorporated with differentiation integration when you're dealing with trig ratios in that aspect. So let's have a look at some example questions, the ones that you are exclusive to this particular topic of trigonometry double angles. However, just be aware that this can be used in other areas of mathematics, particularly at A2 level. So let's have a look at this first question. So in this first question, all it's asking us to do is to express more simply what each of these expressions are actually going to be. So for this first one of 2 sine 15 cos 15, well, for this, what I'm going to do is I'm going to use my knowledge of that sine 2A equals 2 sine A cos A. Now what I'm doing here is I'm trying to find which trig identity resembles this. Now if I then simply replace the 15 with A, and I've got 2 15, so it becomes 2A, then this then resembles this. Now using that, I can see that my A is going to equal 15. So here A equals 15. So then from this, I've got sine 2A, where A equals 15. So that's going to be sine of 2 times 15, which equals sine 30. And that should know the exact value of sine 30, which is a half. Now moving on to B, again I'm going to use my trig identity. So using, for this one, I'm going to use that tan 2A equals, and it's going to be 2 tan A over 1 minus tan squared A. Now from this particular expression I can see that A is going to equal 60. So what am I dealing with? Well, I'm going to deal with tan, well not ta, I'm going to deal with tan 2A, where A equals 60, so that's going to be tan of 120, and tan of 120, if you look at the graph or use CAS, whichever floats your boat, is going to give me an answer of minus root 3. And finally, moving on to C. Again, what I will do is I want to see, out of all my trig identities, which one looks familiar to this. Now again, from this, what I'm going to do is I'm going to use the trig identity that I've spot, which is cos 2A equals 2 cos squared A minus 1. Now in this, looking at the comparisons, A is going to equal 25. So all of this is going to be equal to cos of 2A. Now if A equals 50, that's going to be the same as cos 50. Now do I know the exact value of cos 50? No, I do not. Now again, if I look at my exact values, I've got 0, 30, 45, 60 and 90. Now using any of these 5 numbers, there's no way of me working out what 50 to get 50. So for example, 90 take away 30 is going to equal 60, 90 take away 60 is going to give me 30. I've got another 45, so there's no way of doing it. So what I'm going to do is I'm just going to leave my answer as cos 50. So let's have a look at our next example. So in our next example, this looks very, very similar to our compound angle, and that's exactly how we need to approach it. Now for this, it tells us that you are given that theta is acute and that sine theta equals 4 over 5. Now the main difference with this and what we've been asked to do is to find what sine 2 theta is and cos 2 theta. Now unlike the compound angle questions where you were given a sine theta and then let's say sine A and then we were given cos B, work with 2 triangles. With this, because we work with double angles, we don't necessarily need to know what the other triangle is actually going to be, because I'm going to be using and manipulating my trig identities of these double angles to work out what they are. So for this, what we all need to do is, to start off with, is to draw a triangle. So drawing my triangle, where I've got my theta, and I know that sine theta equals 4 over 5, and it's acute, so it's going to be a right angle. So from this, we know that our opposite and our hypotenuse, so the opposite is going to be 4, hypotenuse is going to be 5, and then using Pythagoras, I can work out what the other side is going to be, or the adjacent in this case, which is going to be 3. So here, I know that from this, that cos theta is going to equal 3 over 5. Now then, from this, what I'm then going to do is, so from what I then want to do is, well, step 2 was to find the missing side, and then step 3 is to work out what sine theta is. Now in terms of step 4, so from this I'm going to use my trig identity of that sine 2 theta equals 2 sine theta cos theta. Now from this I know that sine theta is 4/5, so let me just write that down. So sine theta is 4/5. So I've got 2 times sine theta, which is 4/5, times cos theta, which I've worked out as being 3/5. And if I then work that out, that gives me an answer of 24 over 25. So here, sine 2 theta equals just that. Now in terms of finding out what cos 2 theta is, well, there's several ways in which I can work that out. So cos 2 theta, well, that's going to equal either 2 cos squared theta minus 1, or what I could do is use 1 minus 2 sine squared theta. Now it doesn't really matter which one you've got, but remember that cos theta equals 3/5 and cos squared theta means, so cos squared theta equals cos theta squared. So from this, if I then use that cos theta equals 3/5, and what I get is that cos 2 theta, let me just get rid of that arrow, is going to equal 2 lots of 3/5 squared minus 1. Now from that I can then work that out using my calculator, and it gives me minus 7/25. Alternately, what I could do is I could use, let's get a different colour pencil using this, so I know that sine theta equals 4/5. So here I could do 1 minus 2 lots of 4/5 squared, and that will give me the exact same answer of minus 7/25. So whichever way you want to do it, it's going to give you the same answer. So let's have a look at our third example. So in our third example, the question is asking us to solve the equation of sine 2 theta equals cos theta for the range of 0 and 360. Let me just quickly get rid of that underline. Shouldn't be there. There we go. And inclusive of the values of 0 and 60. Now, because again, always remember the basics. So for this, we are working in degree mode. So always make sure that your calculator is in degree mode and not in radians. Now, in terms of this, and when we come to solving it, what we're going to do is, we know that sine 2 theta equals 2 sine theta cos theta. So swapping that in, what we then get is, and again, all I'm going to do is I'm going to swap that for that. So what I've got is I've got 2 sine theta cos theta equals cos theta. Now from this, what I can then do is, now as there is no mention that cos theta is not equal to 0, I can't divide by both. Now at this particular thing, there's no mention, so let me just write that down. So as there is no mention that cos theta cannot equal 0, you cannot simply divide both sides by cos theta, because it'd be very tempting to think, oh right, there's cos on both sides, let's just divide both sides by cos so that they both cancel out. But unfortunately we can't do that, because cos theta can equal 0 between the range that we've been given here, so therefore we can't. So what we'll do instead is we're going to take this cos theta over to the side. So what we've got is we've got 2 sine theta cos theta minus cos theta, and that's going to equal 0. Now from this, what we can then do is factorize. So with respect to cos theta, so I've got cos theta and then 2 sine theta minus 1 equals 0. Now if you were to divide by cos theta, basically what's going to happen is you're going to lose a set of values. You'll only end up with 1. And that's where the biggest problem is. So if we did divide by 0, all we'd end up with is 2 sine theta minus 1, and we could only solve that, we'd miss this value here. So from this, either cos theta equals 0 or 2 sine theta minus 1 equals 0. Now going on to solve this, where in the region of 0 and 360 is cos theta equal to 0? Well, it's going to be at 90 degrees and 270. Now if I then go on to solve this, so here what I end up is with sine theta equals half, and then go on to solve that, I get theta equals 30 and 150. Now it's always good practice to try and write down your final answer all in one line. So my final answer is going to be 30, 90, 150 and 270 degrees. Now, does it need to be in numerical order? No, it doesn't, but you want to make sure you're including all of those 4 angles, and any sort of missing of those 4 angles would mean you could basically be penalized losing a mark. So let's have a look at our next example. So here what we're moving on to is trig identities. So here we're going to prove the identity that cos 2 theta over cos A plus sine A equals cos A minus sine A. Now in terms of this, again, what we want to try and do is pick one side. So from this, if I just move this up so we've got a bit more space, so what I'm going to do is I'm going to take the left hand side. Now if I just write that out, so I've got cos 2a over cos a plus sine a. And what I'm going to do is I'm going to use the trig identity for this top, because there's not much I can do with the bottom, but there is certainly something I can do with the top. So taking this, what I'm then going to do is change that into a trig identity. Now I'm going to use cos squared a minus sine squared a over cos a plus sine a. Now before you start thinking, why have I used cos squared a minus sine squared a? And the reason for that is I'm noticing this. Now obviously I want it to make it look like cos a minus sine a, and from this I'm thinking of dots. So by taking this particular, the numerator, I can see that that is going to be equal to cos a, if I just set up my double brackets, so I've got cos a, and then I've got sine a, I've got a plus and a minus, and I've still got that denominator of cos a plus sine a. Now although there's no brackets, I'm going to put brackets around that, because from this you should be able to see that those two things cancel. So what I'm left with is cos a minus sine a, which equals the right hand side QED. So now let's have a look at our final example. So again, we've got another trig identity, which in this case here, rather than have a double angle, we've got a triple angle. Now in terms of this, again, I'm going to take the side that probably looks more complicated, although this one, it doesn't look as complicated, but I'm going to take that one anyway. So taking the left hand side, I've got cos 3a. Now what does cos 3a look like based on what we've already done? Well, I can see that cos 3a is the same as cos of 2a plus a. Now from this, I'm going to use my compound angle formula, that cos of 2a plus a. So 2a is going to be my alpha and a is going to be my beta, or a and b, whichever you prefer. So here from this, using trig identities, I've got, I'm going to use yellow, I've got cos 2a cos a minus sine 2a sine a. Now from this, what I'm then going to do is I'm going to take this and use this and this as their trig identity. So rather than using cos 2a, what I'm going to do instead is I'm going to use cos 2 cos squared a minus 1, and I've got a cos a there. And instead of using sine 2a, I'm going to go for the trig identity of 2 sine a cos a, and then sine a is there. So all I've done is just swap those two. Now again, if I then expanded the brackets out, what do I end up with? Well, expanding those brackets out, I'm going to end up with 2 cos cubed a minus cos a minus, and it's going to be 2 sine squared a cos a. Now from this, what I can then do is I'm then going to swap, well, I'm going to keep the for this and this the same, but what I'm going to do is I'm going to get rid of this sine squared a. Now for this, what I'm then going to do is I'll just change the colour, and let's get the pink. So for this, what I'm going to do is I'm going to change that for, well, not actually all of it, I'm just going to change this sine squared a, and instead what I'm going to do is I'm going to write 2 cos cubed a minus cos a minus 2 lots of, it's going to be 1 minus cos squared a, and then cos a. Now the reason for this is because I'm just going to try and get all causes, because ultimately what I want to try and do is, if I look at the right hand side, there's no sines in there, so that's the reason why I'm getting rid of that sine squared a. Now from this, what I can then do is, I'm struggling for space, let me just move down slightly, is that this then is all going to equal 2 cos cubed a minus cos a, then it's going to be minus, and then it's going to be, well, if I just rearrange this, so just have the, move the cos a to the front, just so that when I expand it out, it's going to make perfect sense to you. So that's going to equal 2 cos cubed A minus cos A, and then minus 2 cos A plus 2 cos cubed A. Now let's then try and neaten all of this up. And what do we find? Well, I've got 2 cos cubed and another 2 cos cubed. So joining those two things together, I get 4 cos cubed A. And then if I then join these two things together, I end up with minus 3 cos A. And that equals the right hand side QED. And there is our final example done. Now you will find that a lot of the double angle questions will kind of resemble these, but again, the one thing you need to incorporate is remembering the trig identities and that this area of trigonometry is overlapped with integration and differentiation. Now, talking of integration, there are some half angle identities that you may want to have in your itinerary, and that is that the following half angles. Now, this generally applies when you are integrating, so will come into question later on in the course, but this is certainly something that if you do spot half angles, then you will be expected to know these off by heart. So it's definitely worth making sure that you've got these to hand and in your notes when working with double angle and half angles whenever you spot this, because it will make it a lot easier for you to then go on to either prove or integrate an expression.